The Morse Theorem is what we're talking about today in finding roots of these complex numbers. The Morse Theorem, I believe, is in your reference booklet. It is a way to, it's something that can be used to find roots. It can also be used to evaluate expressions as well. So we're talking about the Morse today and finding roots. Here's the Morse Theorem, okay? So essentially you have this polar form where you have your modulus cis theta raised to a particular power. That power essentially gets applied to the modulus and then it gets multiplied to the angle of theta for all n that are elements of Q. Q stood for what? Ooh. Not quotient.
Fractional numbers.
The numbers that can be written as fractions. Rational numbers, yes. There we go.
Why isn't it R?
All right.
Because
real is R. We're going to find the exact value of the square root of 3 plus I to the 8th power. So instead of doing binomial expansion and having to deal with combining like terms, or even multiplying the square root of 3 plus I by itself 8 times, we can apply DeMoivre's theorem to actually find the exact value of this. Okay. So, excuse me. So what we need to do though first is we need to take it out of its Cartesian form, rectangular form, and put it into polar form. That's what we did yesterday. Okay, remember that's when we took the modulus and then cis theta. So we need to figure out the modulus of this problem. How do I find that again?
A squared plus b squared under a root.
A squared plus b squared under a root. A is what?
Square root 3.
So I got root 3 squared plus what's b? 1 squared. When I square square root, it goes away. So this is nothing but the square root of 4, which is 2. Then I need to find my theta, which is the tangent inverse of what over what? 1 over square root of 3, which is just the same thing as saying the tangent inverse of root 3 over 3. And where between negative pi and positive pi, more specifically, which quadrant? First quadrant is tangent a root 3 over 3.
Root 3 over 3 is 3 over 2 and 1/2. Yes.
Root 3 over 2 and 1/2.
So it'd be pi over 3. Yeah. Yes.
You're looking for this coordinate. It's not pi over 3. Pi over 6. All right. Yep. This is x. So.
But you're doing the tangent of what would be the.
Oh, I put it the wrong way.
Sine over cosine.
You're right. Got it now.
Okay. All right. So this becomes modulus 2 cis pi over 6. This is being raised to the 8th power. So applying the Morris theorem basically says you take your modulus, you raise it to the 8th power, and then you take that value, that n value, and you multiply it to your theta, which is pi over 6. First off, 8 pi over 6 simplifies to be what? 4 pi over 3. And this is non-calculator. What is 2 to the 8th power?
Is it 256?
It is 256. A long time ago, I told you guys you should know your powers of 2, at least up through 7. So then you just have to take 128 and multiply by 2 again, and then you get 256.
Oh.
So then you actually work this out. Remember, cis stands for cosine theta plus I sine theta. So I have what's happening?
It doesn't exist. Would that be a negative?
No, it's in this third quadrant.
Sort of exists.
It doesn't exist.
Numbers are gonna be negative anyway.
Dude, Logan, what are you talking about?
What's the cosine of 4 pi over 3? Negative 1/2. And what's the sine of 4 pi over 3? So with the I, so then we just distribute over. What's half of 256? And so then it's going to be a negative because it's a negative 2. So negative 128 minus 128 root 3 I, and that is the exact value.
Oh, never mind.
So by considering cosine 2 theta plus I sine 2 theta, deduce the double angle formula for cosine 2 theta and sine 2 theta. Okay, do realize that cosine 2 theta is associated with the real aspect of this complex number, and sine 2 theta is associated with the imaginary part. So when we actually take this expression and work with it, once we get what we end up with, we'll end up having the real part associated with cosine 2 theta and the imaginary part associated with sine 2 theta. So hopefully you recognize that this is just a tad bit altered from our normal cosine theta plus I sine theta. Okay? Huh?
Yes.
Yes. Okay? So it's not cis theta, it would be cis what? It would be cis 2 theta. And if you recall from the Morse theorem, that 2 essentially represents what? It represents the exponent. So this can be written
Ooh, yeah.
This squared.
as cis theta squared, which means cis theta, which is cosine theta plus I sine theta, can be squared.
No.
So essentially what we're doing is we're working our way kind of backwards with the Morse theorem. So if I have cosine theta plus I sine theta squared, I'm essentially multiplying it by itself twice. Which means I'll need to do what? Cosine theta times cosine theta. Then I'll have I cosine theta sine theta. Then I cosine theta sine theta, which makes and then what's I sine theta times I sine theta? It was having the I squared sine theta, but I squared is -1. So this is technically a minus sine theta, or sine squared theta, my mistake. And if I put my real parts together, that's cosine squared theta minus sine squared theta, that would technically go together. And then I'll have my imaginary part of 2I sine theta cosine theta. Does this look familiar?
Yes.
What's cosine squared theta minus sine squared theta? This should look familiar. It's not 1, that's sine squared theta plus cosine squared theta. But when you subtract cosine minus sine, that actually equals,
Then
it's actually cosine 2 theta.
No more.
was that also another thing?
And then what about that back part, that imaginary part?
It's a sine square.
Uh-huh. Because essentially this is 2 sine theta cosine theta times I, and there it is. There is sine 2 theta. So we were able to deduce the double angle formulas by taking that complex number.
Whoa, okay.
It's like your proof.
Glad it all worked out in the end.
That's the Morse. Question on the Morse. All right, we can use the Morse when we're solving a particular root of a complex number. So when we're solving a complex number raised to a particular power equals C, the nth roots of a complex number C are the solutions of Z to the n equals C. These bullet points down here essentially kind of let you know a few things that are true when it comes to the roots of complex numbers. They're exactly nth roots of C. So whatever n is, that's exactly how many roots you'll have of that complex number. If C is real, then the complex roots must occur in conjugate pairs. In other words, you're going to have like whatever complex number you end up getting, its conjugate also too will be a root. If C is not real, then the complex roots do not occur in all conjugate pairs, meaning that, let's say it's not, then your conjugate pairs might not be a root as well. The roots of Z to the n will all have the same modulus, which are the modulus of that complex number raised to the 1 over n power. On an Argand plane, the roots lie on the circle that has a radius that is the length of the modulus. The roots on the circle will be equally spaced out around the circle, so they'll go in a respective interval. And if you join all the corresponding roots, then it actually creates a regular polygon when it's on the circle, because they all will be equally spaced out.
Well, regular polygon is straight lines, right?
Straight lines, all the sides are equal and all the angles are equal. So depending on how many you have, if you have 4, then when they're spaced out, they will create a square. If you have five, which probably won't be possible, if you have 6, you'll end up having a hexagon, and basically an inscribed hexagon. That will be regular, equal size, equal angles. That could potentially build to more questions to follow after that. Yeah. All right, so let's look at some examples too, actually a couple, all right? We're gonna find the 4th root of 1 by the n roots method, okay? Because yes, you could actually do this through factoring. You could actually do this through factoring this particular problem. The one thing is that sometimes that when you do it through factoring, it could be tedious, even potentially very difficult, okay? So using the method that we're going to use for this example and the next one, potentially be easier, okay?
Wait, so we're factoring out 1?
We're finding the 4th roots of 1, yes. But remember, if we're dealing with the 4 4th roots, that means that essentially we have C raised to a power is equal to C. N would be what? 4, and C would be what? 1. Now, granted, this could be solved through factoring. This particular one could be solved through factoring and actually probably be pretty simple. What you could do is you could, subtract over the 1, and then you could recognize that this is difference of perfect squares. Factor, continue to factor, and then you could get your roots, okay? Examples like this, yes, factoring would be probably easier than with the process that we're about to go through, but it's actually not as challenging as you may think it is, okay? So I'm gonna erase this because we're going the nth roots way. So what we need to do is we need to get our complex number into polar form. So when we get into polar form, then we'll be able to apply the Morris theorem and get our roots, okay? So 1 is written how? In polar form. So it'll be 1 plus 0i as the complex number. Okay, so I need a modulus, which is clearly going to be, and now I need a theta, which is going to be what?
Tangent of 0 to 1, 0. Which is, no, it's just 0 or pi? Yeah,
Zero can't be on the bottom, so.
well, I know, it's
So
on the
then
bottom.
the sign can.
Look at where it's located. Where's it located? So my angle is going to be 0. Okay, but you need to take into account that we're finding multiple roots. And so we need to actually apply one of our properties of cis that we learned yesterday. This one. Okay, we need to apply this property here. We know our theta, okay, because technically this would be cis theta or cis 0. It is equivalent here. We want to use this part of this property in order for us to find all of our 4 roots. Okay, so cis theta is equal to cis theta plus 2k pi. So here we're going to do cis 0 plus 2k pi, or essentially just 2k pi. If we just did 0, we would not be able to find all 4 of our roots. So we applied the property that's going to allow us to get multiple roots by adding multiple angles of 0 radians.
Okay.
So that's saying that's going to be 2 pi and 4 pi and 6 pi. That's how we'll be able to get the 4 roots of 1. So from here, what we're going to do is we need to get rid of that 4th power. So by doing so, we would take the 4th root of both sides. Which is equivalent. Which is equivalent to the 1/4 power. Remember, to do DeMoivre's, we need an exponent, not a root.
Making sense?
Now we're able to apply the Morse theorem, which basically says our modulus raised to the power times cis in theta. So then I'm going to apply 1/4 to my modulus, which is 1, but that's just going to be 1. And then I'm going to multiply 1/4 to my angle. Well, what's 1/4 times 2k pi? K pi over 2, and this will just turn into 1 still. So we'll have like so. And now that we have our complex number, we've applied our 4 roots, we're able to find what they are. How do we find our 4 roots? This is when we use that property where k is an integer, and we plug in 0, 1, 2, and 3 to get our 1st root, our 2nd root, our 3rd root, and our 4th root.
Why is 0, 1, 2, and 3 not 1, 2, 3, and 4?
But you can't forget about 0. Because the integer could be 0, and then 1, 2, and 3.
So you start at
Your first 4. Huh? Mm-hmm.
You always start at 0, okay?
Yes. So then you'll plug in 0, 1, 2, and 3, and you'll have your, and then once you apply your cis, then you'll be able to find your roots.
So we're supposed to do the cis of like table all those?
Mm-hmm. So that's going to be cis of 0 times pi over 2, which is just 0. We're going to do the cis of pi over 2, the cis of pi, and then the cis of 3 pi over 2. And this is how we'll find our 4 roots, our 4 4th roots of 1. Since of 0 is nothing but cosine of 0 plus I sine 0. What's the cosine of 0 radians?
1.
And the sine of 0 radians? So this is just 1. So that's one of my roots. Over here, this is cosine of pi over 2 plus I sine pi over 2. That's just what? I. So that's another root. Then I'll have the cosine of pi plus I sine of pi, which is, that's another root. And then cosine of 3 pi over 2 plus I sine 3 pi over 2. And these would be our fourth roots of 1.
Together.
Oh, no, we just list them?
Yep, because it's asking for the roots.
Multiply them all together.
We're gonna find the fourth roots of -4 in the form of a plus bi. No, it will not always be 4. Sometimes it may be the cube root. It could be the 5th root. They just have both to be 4.
What do you think the highest one we'll have to do is?
Probably 4.
Okay.
After we do that, then we're gonna write z to the 4th plus 4 as a product of real quadratic factors. That's actually going to do a throwback to that fundamental theorem of algebra that we learned back when we were talking about quadratics. I think last year, to be honest.
Oh.
All right. So we're going to find the fourth roots of -4 in the form of a plus bi. So we're going to start out by writing it as z to the what power?
4.
Equals -4, okay? Then we want to put this into polar form. -4 is basically -4 plus 0i. What's my modulus going to be?
4.
4. And then what's my angle going to be?
We're gonna have to do the weird fancy trick again.
No, not 0. Think, where's -4 a lot on a Argand plane?
Oh.
It's gonna be on the negative, not the negative I, the negative R axis, because it's -4. That's the real part. So what's that angle right there? It's gonna be pi, okay? And then we'll have our plus 2k pi to allow us to get our multiple roots. And then what we did before, we got rid of that exponent on our z by taking the fourth root, AKA raising the other side to what power? The 1/4 power. And then from here, we apply the Morse, which basically says we take our modulus and raise it to that power. And then we'll take our angle and multiply it by that power. So this essentially is going to be pi plus 2k pi over 4 when we multiply it. This is a non-calculated problem, if you're wondering. Okay. So we can plug in our values for k, starting where? Starting at 0, and we're doing 4 roots, so that's going to be 0, 1, 2, and 3. The only thing right now is that we got this here. 4 to the 1/4 power. That can simplify. Anybody want to take a stab at how that simplifies?
2.
Not 2 root 2, not cube root of something. It would be the square root of 2.
Yeah, okay.
It would be the square root of 2. If you're not seeing it, look at it like this. 4 can be written as 2 squared, being raised to the 4th power. A power to a power you multiply. So then you get 2 to the 1/2. 1/2 as a root. It's the square root of 2. So I'll have the square root of 2 cis. When I plug in 0, this will basically be pi over 4. Root 2 cis, when I plug in 1, that's going to be 3 pi over 4, because that'll be pi plus 2 pi over 4. When I plug in 2, 5 pi over 4. And then when I plug in 3 for my last root, it will be 7 pi over 4. Find my 4 roots. So doing this out, my first root is going to be
1 plus I?
1 plus I. My second one,
Negative 1 plus I, or 1 minus I, or I minus 1.
What?
Write down I.
I'm gonna write it in the form of A plus BI.
Okay.
Yep, What's the next one?
Both negative. 1 minus I.
So then those are the 4th roots of -4. That'll be our answer for part A.
But wait, there's more.
There is more. That incorporates older concept back from when we were doing polynomials, because it says hence write z to the 4th power plus 4 as a product of real quadratic factors. When you think of a quadratic, right? And when we used to factor them, we always look for 2 numbers that did what? When we were factoring a quadratic. Multiply to give us
Oh, C.
the C,
Add together, give you B.
add together to give us B,
B.
right? So the thing is that when you look at these roots, they're conjugates of each other, right? Like this one goes with this one, and then this one goes with this one, correct? So if I take the 2 conjugates that go together, if I were to multiply them together and then add them together, wouldn't I get my B and my C of my quadratic? 1 plus I, 1 root, plus the other root. Because remember, we always look for 2 numbers that essentially would be our solutions that multiplied together that gave us C, added together give us B. So if I were to add these and multiply these, I would essentially get my quadratic without having to do the old school, write them as factors, do this excessive foiling, and then multiply them together. Because we just want them as the product of our real factors. So what's 1 plus I plus 1 plus 1 minus I? 2. And then what's 1 plus I times 1 minus I? B2 again. So then we'll have Z squared plus 2Z plus 2. That will essentially represent the quadratic of those 2 roots. I can do the exact same thing with the other 2 roots that go together, add them, and multiply them. And then again, I will get the 2 numbers that would, or the number that when I multiply them is my C, when I add them is my B, which gives me my other quadratic. So what's -1 plus I minus 1 minus I? -2. And then what happens when I multiply them together? (-1 times (-1) is a +1,
times the negative I squared.
plus a -I squared, which gives me a +1, which gives me 2. So then I'll have z squared minus 2z plus 2. That represents these two roots. And together, this quadratic and this quadratic, when I multiply them together, would give me z to the 4th plus 4. I'm not going to do that because it's asking me for the product of my real quadratic factors, and that would be my answer. But if I were, I would have z to the 4th, everything in the middle cancels out, and then 4 at the end. And that's the last bit of complex numbers with the Morris theorem. Find the roots,